Welcome, everyone. Thanks for coming to this last session of the day. Appreciate you all being here. I'm going to talk today about Your Containers Aren't Alone, Demystifying Container Isolation. So first, a little bit about me. I am a research scientist at Edera, a startup that works in kind of the hardened runtime space, making container images more secure and really kind of fully isolated in their own way. Outside of that, I also am one of the co-chairs of the Cloud Native Computing Foundation's tag security and compliance. Sorry, it's a bit of a mouthful, but we basically work on doing security assessments and providing security guidance for CNCF projects, as well as just kind of for the ecosystem as a whole through CNCF projects, right? I'm also a maintainer of a few open source projects, most notably the Update Framework, or TUF, which is a framework for secure software update and delivery. Nothing to do with what I'm talking about today, but another thing that I do. And before I was here at Edera, I was working on my PhD at NYU. So doing a lot of work in kind of software supply chain security, as well as open source security space. So that's enough about me. Let's talk about containers. And this is, don't worry, the whole talk won't be this. We're starting from here so that we can kind of work our way up to other stuff. And hopefully it'll still be at a bit of a high level, but hopefully still interesting for all of you. But in case anyone's coming here who hasn't heard of containers yet, or this is new to them, a container is a unit that packages up code and everything that's needed to run the code, including libraries, dependencies, configuration. It kind of solves the "it runs on my machine" problem, right? If you've ever written code and then tried to give it to a friend and it didn't work for them, this kind of solves that problem, right? You write the code, you make it run inside a container, you give that container to your friend, and the code will run on their machine. And not just your friend's machine, but also in production on all kinds of different systems. And containers run in the operating system, kind of similar to processes, with tools like namespaces and cgroups, which we're going to talk more about in a minute, providing them with their own kind of view of the kernel, so they can access resources and use them as such. Why do people use them? They're lightweight, which means you can run many containers on the same system to make efficient use of resources. This is, the cloud resources can be expensive. Physical compute resources can also be expensive. And so containers let you just plop a bunch of programs, again, in this kind of box onto the same system. They're also portable. A container that works in your local environment, this is like we were talking about, will also work on your coworker's environment or in production. They start up and shut down fast because they're running on top of the kernel. Your production application can just add or remove more containers as that scale is needed. And they have a standard format that gives you access to an entire ecosystem of tools for things like container orchestration, stuff like Kubernetes. This all works because we have these standard formats. So what we're going to talk about today, though, is not just containers, but containers running in what we call multi-tenant environments. This is containers from different organizations or different users of the same organization who maybe themselves are at different organizations, sharing the same infrastructure. And this is great for resource efficiency. As we were talking about before, you only have to access and pay for the computing resources that you are using, even if there's all these other people on the same machine. And because of this is kind of a fairly popular pattern. But you don't always want your data to be accessible to all these other users on the system. So in using containers for multi-tenancy kind of exposes some of the unspoken assumptions in containers. They look like their own view of the operating system kernel, but they are fundamentally running on the same operating system kernel, right? And this means that if other mechanisms, which we're going to get to, are not in place, containers can view or alter workloads running in other containers. This is a problem both for security, because obviously if you have data in your container that you don't want other people to access, but also for performance, because you don't want one container to just take all of the CPU resources for itself and leave your container kind of out in the cold, unable to do any processing work. So you can have someone else is in that other container. And what we need, what we're going to talk about today, is some mechanism, which we're going to go into, to isolate containers from each other. Put the box inside a box that's actually kind of a security boundary around the container, and to isolate them from each other, and in some cases even from the host operating system itself, which may be a third-party cloud provider or somebody else that you don't necessarily trust with your workloads or with your data, especially as we start coming into the world of AI and AI workloads, right? You want to make sure that your models, your data are protected. And you want to prevent these applications from escaping, a term you may have heard, or interfering with other containers. This is right. Never mind. Sorry. I was like, there's nothing on that slide. It's going to appear. To illustrate why we need container isolation, this is going to be a few examples of container escape vulnerabilities from the past year or so. Won't go into too many details on them, but this is just showing that these do happen. And so if you're running containers in multi-tenant environments, this is probably something you should be thinking about. This one here is a vulnerability which allows containers to mount the host file system onto build containers. The container then can have read-write access to the host file system, which is a container escape. This one here is a vulnerability in NVIDIA Container Toolkit, kind of in the AI space, that exploits a time of check, time of use vulnerability, so that a specially crafted container can gain access to the host file system. Starting to notice a pattern. This one here, Leaky Vessels, is a container escape in runc and buildkit that enables an attacker to gain access to, again, the file system. They're not all file systems, I promise. This one here is a set of CVEs in the network orchestration platform, the specific network orchestration platform that exploits various elements of the platform, which together can let an attacker compromise both the application and the host operating system. This one's Docker Desktop, lets local Linux containers access the Docker Engine API, execute privileged commands, including controlling other containers and sometimes access to the host file system. And finally, another one in NVIDIA Container Toolkit that exploits a few flaws in the hooks used to initialize containers, which can lead to a privilege escalation. And I mention all of these not to call out any of these companies or technologies. They all do great work, but these things are hard, right? And this kind of illustrates an underlying problem with some of the assumptions we have about containers that can be broken when security flaws like these are found. So just kind of to set the stage. Let's talk about container isolation and different mechanisms that are in place. I'm going to kind of group these into 4 categories for the purpose of this talk, just to talk about different ways that isolation can happen. Application and service isolation separates kind of workloads and APIs using things like dedicated namespaces, things like that. Runtime isolation enforces boundaries in the compute environment, things like a hypervisor that separates it at the runtime. Node isolation uses dedicated nodes to isolate workloads. I do have a slide about this, but it's less a technology more than a method of using containers. And then finally, we have hardware and physical isolation, which create physical boundaries between the workloads, which things like air gaps or confidential computing that kind of do more hardware-based security. And of course, I think one thing that's really important to talk about here is that isolation is not the only thing you care about when deploying your application. I think as someone with a security background, it's always easy to say what you want is the strongest isolation. You should put all your containers on their own computers in their own spaces. But obviously, that's not always practical, right? We also need things like performance and the cost associated with that performance, right? The hardware requirements that might be introduced by an isolation tool. How expensive is that hardware? How much of it can you access? Compatibility with existing workloads and tooling. Do you have to rewrite your whole application to use this tool? Is that feasible? How much do you have to rewrite? And each of these factors can be more or less important depending on how sensitive your application is and its data, also the environment and how much, and who else is actually on the machine, and more. So these are just kind of things to keep in mind as we go through some of these technologies. Okay, and we're going to go through a bunch of technologies in each of these 4 spaces. This is not a comprehensive list. I just want to say up front, I tried to stick with open source technologies for the purpose of our open source summit that kind of illustrate this. And so let's get into it. First, we'll talk about namespaces. I think this is the big one, right? That I think probably the first one a lot of folks become familiar with. So namespaces create distinct contexts within the kernel for each container so that each container sees a different set of resources on that kernel. There are a lot of different types of namespacing, and I'm not going to describe the details of all of them. There's great write-ups and stuff in the space. But there are types that create a context for specific resources, including things like process IDs, networking, or like user namespacing. And these are all a feature of the kernel, and they rely on kind of kernel mechanisms to provide these kind of namespaces. C groups, similarly in the Linux kernel, it's a Linux kernel feature, also available sometimes in other kernels, but we're talking about Linux here today. And they put limits on the resources like CPU or memory to prevent some of those things like a noisy neighbor, right? So if you have two different containers, one of them really wants to use all this CPU for its stuff, but the other container still wants CPU. So basically this means that each container is given access to a specific amount of CPU, and they know that they'll have access to that. Next we have seccomp, which is another Linux kernel feature. This one restricts system calls rather than the resources, and this really limits kind of the attack surface within the container. Because if you limit the syscalls that are available, you limit what people can do, and this can prevent a lot of attacks, similar to other allow list type technologies, right, where you know what people are allowed to do. Capabilities, also in the Linux kernel, so I think seccomp is as well. This divides super user privileges into distinct units. This can be used to give containers only the permissions that they need, right? So instead of just saying, you need to be able to do this one thing, we're going to give you all root privileges, why don't we just give you that one thing? It's just kind of similar to seccomp. It's just a way to limit the attack surface within the container. And finally, in this category, we have SELinux and AppArmor. So SELinux, or Security Enhanced Linux. These are both technologies for mandatory access control, which add mandatory access control, again, to the kernel to define a policy for which applications, processes, or files that container is allowed to access. And these are somewhat similar but different technologies. I won't get into the exact details, but they both do this mandatory access control piece. So a quick summary of this first category that we're talking about, this application and service isolation. Most of the ones that we talked about here are features of the Linux kernel, right, because they're operating at that level of the stack, right, and the containers are still operating on the shared kernel. These are pretty low overhead additions to your kernel, and you can layer them all together, right, to get all those different protections that we just talked about at the same time, in most cases. So that's kind of the benefits there. And we'll talk more comparing all of these at the end. The next category we have is runtime isolation. So to start with, we'll talk about gvisor, which is a container sandbox that provides a user space application kernel. This is going to be a little bit different than the other technologies in runtime isolation we're going to talk about, in that it operates in user space, right? So we're still working on top of the kernel here. And it provides kind of an extra layer of protection between containers and that underlying shared kernel by kind of trapping a lot of stuff, but still in user space. And this is able to prevent a lot of known attacks on isolation because more so than the previous technologies we talked about, operating at this runtime layer, you're able to just trap more things and access more things at the same time. But there is still that kind of underlying shared kernel. And every now and then, I think there you get some really, really clever attacks that are able to get past the gvisor sandbox and into the shared kernel. But it adds a much harder boundary between it. Sorry, was there a question? No, okay. So once you get past gvisor in this runtime isolation space, we're going to have to start talking about virtual machines. Hopefully we won't scare anyone away with the next couple slides. But yeah, a virtual machine, as you may be aware, has a separate operating system kernel for each workload, which provides a very strong layer of isolation because you have a whole different kernel for each workload. And to do this, you have what's called a hypervisor, which runs on the hardware or the host operating system and enables a virtual machine monitor, which is sometimes considered part of the hypervisor, but I'm going to separate the concepts for reasons that will become clear later. I think it just makes the technologies easier to understand. And the virtual machine monitor mediates all the access to the CPU and memory. So the guest operating systems really can't access anything from the operating system itself without going through this VMM, which is kind of a clean isolation boundary. But traditionally, virtual machines were kind of clunky and designed for things like dual booting, a single personal laptop, or for like application testing on different systems. Running an entire operating system just to run your one workload, it doesn't make much sense in reality, which is why they invented this thing called the micro VM. So micro VMs have the same kind of general principles as virtual machines. You see the diagram looks mostly the same, but the kernel is different. And I maybe should have used a different word in the picture. It's more like a lightweight kernel, right? That's the whole idea here. Those guest operating systems are more lightweight and do all kinds of optimizations, including some clever things like putting duplicate operating system kernels in like read-only memory that all the different containers can access, right? So you're really saving space in that way, even though you have all these different machines. And different technologies in this space have enabled a lot of cool features like much faster startup time than kind of traditional VMs and support for container runtimes, which I include in this diagram because this is a talk about containers. So we're going to assume that for now. So first we're going to work our way up the stack here of this micro VM space, starting at the bottom with the hypervisor. The two we're going to talk about today, probably the two most popular, are called Zen and KVM. KVM is a type 2 hypervisor that acts kind of as a module in the Linux kernel and enables the use of hardware virtualization features on the CPU. So most modern CPUs have access to these things called hardware virtualization features that basically enable much more efficient virtualization. So and KVM kind of interacts with those CPU features to give VMs and through them containers a view of that underlying hardware. The tricky thing about that, and I think why I mention it here, is that if you're working in the cloud, even though most CPUs have them, you don't always have access to those features through your cloud provider, right? Is this idea of like nested virtualization, because when you're working in the cloud, you're mostly not. Sometimes you can buy bare metal instances, but if you're not working on a bare metal instance, which tend to be expensive and give you like an entire machine, what you're doing is you're working inside a VM, and then you're putting your VM technology inside of that. And that VM that's provided to you by the cloud provider would have to pass through those CPU features for you to then use them with your VM. So it just kind of depends on where in the stack you're sitting, but that can make a big difference. And Zen is another hypervisor. It's a standalone type 1 hypervisor. It has support for hardware virtualization as well, but it also supports what's called para-virtualization, which doesn't do that hardware pass-through, which in some cases can have performance impacts, but it does work with nested virtualization. And the way para-virtualization works, in short, is that the guest operating systems know that they're running on in parallel virtualized world. They know that they're guest operating systems, and so instead of making system calls, in certain cases they make what are called hypercalls, which are very similar in reality, but it just allows this pass-through to happen. And actually the interesting thing on this slide is that Cody from the Zen project is actually giving a talk at the same time as this one, I think specifically about this kind of Zen KVM difference. So unfortunately you're all here instead, but maybe you can find it online. So anyway, we're going to move up the stack of these micro VMs. Talk a little bit about Firecracker. This is a micro VM that powers AWS, Lambda, and Fargate. This is one of the early ones in the space, and it's really designed for fast boot times and a small attack surface at this VMM layer. They have some pretty impressive startup time numbers for this. Cloud Hypervisor is another VM that's also optimized for cloud-native workloads, backed by Intel and others. I think just depending on the characteristics of applications, these are both interesting. And then going on one step up, on top of your VMM, you have to actually have a container runtime. And Kata Containers is a popular one that lets you run OCI-compliant containers in a micro VM. It uses a VMM like Firecracker or Cloud Hypervisor to interface down to the hypervisor, but Kata Containers manages kind of the container runtime layer in this stack and kind of passing things on to your containers. In addition to these kind of it's hard to call them traditional microkernel architectures, but in addition to those, there are other kind of tricks you can do in addition to kind of traditional virtual machines, and one of those is unikernels. And the idea here is that they're even more lightweight, but kind of at the expense of compatibility with existing containers. So you do have to, so what you do is you compile your application with the kernel, with like a very minimized kernel just for your application to make kind of like a single application mini operating system that you then run on top of your hypervisor. And this provides kind of like similar isolation properties to micro VMs. Each application has its own kernel, but there's a lot of limitations in terms of compatibility and kind of development of these, right? Because you're recompiling your operating system every time you change your application, which, for very specialized applications, this can be super useful, or really resource-constrained environments. But it doesn't work and I call these applications instead of containers because they're really not containers anymore because you're recompiling them for this space. Hyperlight, so WASM is a technology that provides kind of a bytecode sandbox in user space, which also provides isolation. I maybe could have given that its own slide. But then similar to unikernels, applications have to be rewritten to be kind of WASM compatible. But it's a pretty big standard, unlike unikernels, right, where you're doing application-specific rewriting. It's more like a different standard. And Hyperlight is a hypervisor technology, or really a VMM technology, that provides a space to run WASM code inside a hypervisor to kind of that kernel level, so you get that kernel level isolation as well, in addition to kind of the application level isolation that you already get with WASM. So that's another cool technology in the space. So a quick summary here. We have a lot of technologies for runtime isolation. Mostly they work with a separate kernel per container. In case you forgot, at the beginning of this session, we were talking about gvisor, which actually doesn't do that, but still provides kind of this runtime layer isolation. Some of these technologies, you start to get into some of those overhead or compatibility issues. Kind of in exchange for that stronger isolation, you do have to make some decisions about compatibility or overhead. And also overhead differs per application type when you start talking about this. And sometimes you have some light hardware requirements with things like KVM. But we'll get into heavier hardware requirements later, so that's why I call that light. Very quickly, I'm going to talk a bit about node isolation. Really is just one slide in this section, with the idea here being that you separate your containers by node. Basically, you can put each container or each set of containers that you want to isolate. There is a layer here in all my diagrams that's missing about how containers run inside pods, which run inside nodes. For folks who aren't familiar, for simplicity, I don't have all those layers here. But basically what you can do with node isolation is put anything you want to isolate in like the same security context into the single node, and then put that node on its own machine, either its own actual machine or its own hypervisor, which gives you isolation as well. And it does get isolation, but you kind of lose some of the advantages of containers over some of the other tricks. But this is, like, as far as compatibility, this is really nice because you're just using your existing technology stack, but just putting things together in a different way. So moving on from that, we're going to talk a little bit about hardware and physical isolation. So where we get into kind of some of the more complicated but very strong security property technologies, like confidential computing. So confidential computing is basically a technology that can be used for strong isolation by running the container inside what's called a trusted execution environment, or TEE. And a TEE is a special piece of hardware that sits kind of next to your CPU and has features like encrypted memory and the ability to encrypt data and code in use. So not just at rest, not just in transit, but actually while in the memory of the system, the data is all encrypted. In practice, this usually works also with a hypervisor. So you have like a hypervisor tech stack, and then with your container, but the container itself actually runs inside the TEE. And examples of this for containers include projects, open source projects like Constellation and Confidential Containers. There's a whole consortium called the Confidential Computing Consortium as well that has a lot of open source technology in this space, some of which has to do with containers. But yeah, this gives you really strong isolation properties, but of course you need access to this piece of hardware, a TEE. And because it's on hardware, there are some compatibility things that you have to manage, right, in order to run your application in this space. So that was a lot of technologies. Let's take a step back and think about kind of what each of them provide. So we're going to, at this level, we're just going to talk just about the categories. So we have this application and service isolation, things like namespaces, cgroups, seccomp, capabilities, SELinter, AppSec. These all kind of work inside in the kernel to kind of give your application something closer to its own little box, its own little window onto the kernel. Because these are all working at the kernel level, things like kernel CVEs can and have affected the isolation of these technologies. Some of those examples of CVEs at the beginning were of applications that took advantage of these technologies, but there was some bug, either in these technologies or somewhere else in the kernel that gave the attackers, workarounds around these technologies. And so, yeah, that's just something to consider when working only at that space. But again, all of this, but because these are working kind of at the application level, these technologies have probably the least overhead of the technologies that we've talked about. Then we have runtime isolation, things like gvisor, the whole family of micro VMs, unikernels, Hyperlight. These provide a much stronger security boundary because they have their own kernel per application, which gives you a lot of strong guarantees, even against bugs in the kernel itself. But depending on the exact application, they have some amount of extra overhead that you get in exchange for that additional isolation, because you have its own kernel per application, or in the case of unikernels, you have decent performance, but you do have to have some compatibility issues, right? Some additional development overhead that you have. Then we have node isolation, container per node deployment. This, I think, is pretty straightforward, has pros and cons. Pros being you use the technology you have today, super compatible with everything that you do. Cons being that it's pretty high overhead, similar or more so in some cases than micro VM type technologies. And finally, we have hardware and physical isolation, confidential computing, which I had a slide for, air gaps, which I didn't, which is basically just running your set of containers in an air-gapped environment, right? So physically separated from the rest of the internet, which means that the rest of the internet can't interfere with your application because it's physically separate. This gets even more expensive because you then have to have a separate physical machine that you're running it on. But this probably provides the strongest guarantees of any of these things, right? Because if it's air-gapped, the data really can't leak back in a meaningful way. So that's basically what I have here. Hopefully you learned something. Hopefully this provides some framing about container isolation. And yeah, I'm always curious to hear about what folks are doing to isolate the containers, what's going on in this space. And also kind of, as my putting on my hat of CNCF tag security, interested in kind of getting folks in the open source community together and talking about container isolation and also just isolating multi-tenant applications more generally. What are people doing in this space? How can we work together better in this space? So I'll kind of seed that for the questions. And thank you all. And I think we do have some time for questions here. So I don't use testing? No, never mind. You'll just have to shout. So anyone have questions, comments, thoughts? Yeah.
So you mentioned Hyperlight using WASM. Isn't that pretty limited in terms of what you can compile there, or is that improving?
I think it is improving. Sorry, I'm going to repeat the question. Yes, so the question is about Hyperlight and the limitations of WASM, basically, and what you can compile into WASM. And I think that this is improving. I think there's a lot of work happening in the WASM space. But yes, I think that's part of actually where you get some of the security, right, is that it's like a more limited set of operations that are allowed, which means that you can lock it down in a lot of cool ways. So. Yeah, in the back.
Do you know about Warhammer? Can you explain a little bit how that's used and how we
Yeah, so the question is about Rowhammer. And so Rowhammer is an attack on, I'm less of an expert on this, but it is an attack on the CPU itself, which can allow basically, I think, memory leakage between things running on the same CPU, if that is a good summary. And that is a really good question, because I think even beyond having a separate kernel, there's this question of, below that you have a shared CPU when you have these multi-tenant applications. And I think the only thing that you can really do about that would be some of these hardware level things, right? Because everything else is operating on top of the same CPU, right? And so if the CPU itself is vulnerable, you need hardware level protections to get around that, as well as patching your CPU, obviously, for Rowhammer. So. Again, that's one of the benefits, actually, that I didn't mention about confidential computing, is that the only hardware you have to trust is that TEE. You don't have to trust the kernel, the hypervisor, or anything like that. You're just trusting the hardware of the TEE itself and the stuff running inside of it. So, yeah. So yeah, the question is whether the TEE was affected by some bugs in the Intel management engine. And that is a great question that I don't know the answer to. So yeah, it does bring up that like you are still trusting this piece of hardware, right? And so any hardware level bugs in this hardware could still be a problem, right? You have to trust something, basically, if you're running your application. So yeah, I'm not sure about that particular bug in this, though. Awesome. Well, if there's nothing else, thank you all for coming. I'll let you all get to the rest of your day, and I'll be around. Thank you.